And then, so now I'm live. And then I'm just going to check to see if I am live. It probably won't go live until exactly 7 o'clock.
Okay.
So it's not live yet. When it goes live, then I guess I'll start talking. So I have the actual YouTube, like what people see. So you can see that.
Oh, yeah.
Right here that, you know, it's counting down. So it's like 1 minute to go, 1:22, whatever. And yeah, I don't know if it's recording this or not. It records it, the whole thing, but I don't know if it starts recording. Okay, so now we're live. It records it, and I have to shut this down now because it is going to be a problem. Okay. All right, so we are now live. We're live here with John A. Macken, who recently wrote a paper called Oscillating Spacetime, the Foundation of the Universe. And he also wrote a book called The Universe is Only Space-Time. And so he's got a very interesting, I guess, theory of the universe that is based, it's a wave-based model, it's a wave-based theory. And he's basically, today what he's going to do is he's going to present the foundation of his theory. And he's going to talk a bit about how he came to the conclusions that he came to as he was developing his theory. And so John, I can, you can take the stage here and you can start talking about your theory. What I'm going to do is I'm going to put your slides on the screen, and so you can start presenting your work.
Okay, so I'm going to start off by telling you a little bit about how I got into all of this. First of all, my background is lasers and optics. I have like 36 laser related, or 36 patents, maybe 30 of them related to lasers and optics. But and I was the president of laser related companies for over 30 years. And I would be president during the daytime and then go back to work at night and do my inventing and doing all my scientific work. So while I was president, I really only wrote one technical paper, but I was writing all these patents and that sort of thing. But the one technical paper that I did write was a really important paper in the field of lasers and was recognized as being what they call a milestone paper. I came up with an invention that was able to increase double the power of a CO2 laser, if sealed off CO2 laser, and increase the lifetime of the sealed off CO2 laser by a factor of 4. And virtually all of the sealed off CO2 lasers now use my gold catalyst that was in there. So anyway, now after I retired, I actually sold the company and retired. And then I got involved in 2001. An idea occurred to me. And the idea was that I realized that if the light that was inside a laser, in other words, you have two mirrors and the light is going bidirectional inside the laser. So light normally is free to propagate at the speed of light. But when you put it between mirrors, for example, then it becomes confined light and its properties change. For example, waves are going one way and waves are going the other way. And you end up then creating standing waves in this cavity. And what I realized is that these standing waves, or this confined light, had, depending on how you count, between 5 and 8 particle-like properties. In other words, there are properties that are like quantum mechanical properties or relativistic properties that we say, well, that's a mystery. But no, when you look at it as what's going on with confined light, all of a sudden you can begin to understand what's happening. For example, I'm going to enumerate what the properties are. You have a confined light has got a specific frame of reference. When light is free to propagate at the speed of light, it has no frame of reference. But if you put it between two mirrors, it acquires a particle-like property in the sense that you can decide, oh yes, it's right here, or at least it's this frame of reference. So besides the frame of reference, it has relativistic properties. For example, in a moving frame of reference, if you had a ruler and is moving, physically the length of the ruler gets shorter, and this is relativistic length contraction, or Lorentz contraction. Also, if you look at a moving clock, the time slows down. And if you look at the energy of, let's say, a mass, the energy as it's moving increases. Well, the simple formula that you learn in freshman physics is energy equals 1/2 mv squared, mass times velocity squared. But that's just a portion of the relativistic equation that then has the energy increasing virtually to infinity as you approach the speed of light. So this is another relativistic property that you think of as being something that is not conceptually understandable when you're looking at it as just a mass, but in fact it becomes very understandable when you look at it as what happens to light waves, that's waves that are going in both directions. I'll get into that a little bit further. There's another point that the light inside the laser also has inertia. Let's suppose you accelerate that laser. It turns out that there's photon pressure on the two mirrors, and then as you begin to accelerate it, the pressure on the back mirror increases because you get the Doppler shift. You get blue shift for light moving an accelerating mirror, and you're getting red shift for light that is moving the other direction. So then you can calculate the difference between those two pressures, and there's a net force. The net force exactly equals the inertia that amount of energy should have. If you had electrons or particles that had the same energy, they would exert the exact same inertia. So you don't even need a Higgs field for getting inertia into this model of just confined light. So, and then finally, the wave properties of like an electron, they have de Broglie wave properties, and it has a de Broglie wavelength, and then there's two different velocities that the waves have. One's called a group velocity, and one's called a
phase velocity.
Phase velocity, yes, pardon me, you got it. So anyway, then the point is that all of a sudden I'm saying, is this an accident that this confined light has got all of these particle properties, or is this something that's trying to tell me that this maybe has something to do with the way matter is really made? So I'm saying, okay, I'm an inventor. Can I try and see if I can invent a particle, an electron model that captures all of these 6 different particle properties just by being able to somehow make a wave-based model of an electron out of, instead of just saying, oh yeah, an electron is an excitation of the electric field, of the electron field, and the muon is an excitation of a muon field. There's nothing fundamental there that you can then go any further. Whereas when you say we are now going to look at something as if it's waves, once we can begin to calculate the wave medium and the wave lengths and the wave properties, all of a sudden you can begin to delve into the background of how electrons are physically assembled. So in any case, then I'm going to go over to my
I will
first picture here.
So,
and there we go.
There, no, I took it off just to put us
Sure.
on the screen together, so it's good now. Yeah.
So anyway, the paper that I just wrote, and it's really the culmination of over 20 years of work, is Oscillating Spacetime, the Foundation of the Universe. And what I'm really saying is that this thing about the foundation of the universe, right now, the quantum field theory says that there's 17 different fields. You have, like I said, the electron field, the muon field, and you have electromagnetic field. And these fields are all on top of each other, which is aesthetically, it's not very pleasing. And I'm saying, no, when you begin to look at space-time as being this oscillating medium, and I'm going to get into this in a minute, all of a sudden you can discover that all 17 fields can be combined into one field. So I'm saying it's a single field model of the universe based entirely on waves. So right now we say, oh yes, we have particles that have wave-like properties or wave-particle duality. But the question is really, waves and particles are like not really, it's like saying top-down properties. They're kind of opposite. A wave has got a physical volume. A particle is a little point, and it doesn't have any waves associated with it. So I'm saying you really, when you get down to it, the design needs to be either fundamentally a particle or fundamentally a wave and then acquires the other half of the properties. So right now, most physicists say, oh yes, well, there's mainly a particle. So we're going to have this point particle that jumps around discontinuously and makes a wave-like distribution. And that's how we get these wave, when we get these, when we pass an electron through a double slit, we get a wave pattern. And it's just this probability of where we happen to find this point particle. The other alternative is that, no, it's fundamentally a wave that then at the termination, when it gets absorbed, collapses to a smaller size wave and acts like it's a point particle. But even then, it's never a point particle. So now I'm going to go to, let's see if I can, yes. So then I'm now going to say that today's session, I'm going to talk about the properties of waves and the model of oscillating spacetime. And then there's another session that I think is going to happen in 2 weeks, which is really the more meat of the, anyway, this is extremely important what I'm dealing with today, but then I'm going to carry this further and come up with a model of an electron, and most importantly, a model of the forces the electron makes, both the electron charge, the electrostatic forces, the gravitational forces. So I then saying, as you're perhaps listening to this, you're wondering, oh, where is this going? Is this going to end up in anything that gives me some sense that it's really attached to reality? So now what I'm giving you is a little glimpse forward. And after we get through the model of the space-time, the model of electrons, I thought I was finished with my model when I then made an electron model that I got the correct energy for, just using the properties of the model. I'm able to calculate the energy. I got the electron's energy. I got the electron's inertia. I got various other properties of electron. I thought I was finished. But then all of a sudden I realized, wait a minute, there's something more going on here. If I have 2 of these rotating wave models here, there's going to be a disturbance in this medium that's between here, and I can calculate the effect of that disturbance. And when I calculated that effect, I would have ideally liked to have seen it be the electrostatic repulsion, but in fact, it turned out to be related to that. Rather than charge E, it turned out to be the force that you would get if both electrons had Planck charge. Well, Planck charge is 11.7 times bigger than charge E. Planck charge is really the fundamental unit of charge, and charge E is like a scaled back ideal. For example, if you have an electron and it's interacting with a photon, it has a coupling constant of one of the alpha of the fine structure constant. Mm-hmm. And yet Planck charge has a coupling constant of 1. So you end up really with what I was calculating was what the force would be if I had a coupling constant of 1. Well, that's a success. Okay, well, I thought that's really great. Then I said, something, is it possible that I have another force happening here that would be a nonlinear effect that would be really small? And it turned out, yes, I get gravity out of this. I got the gravitational attraction. I didn't even need to make any adjustments like I did in the electron. I got it perfectly. So then what happens is that as I then go through there, I find that all of a sudden I get new equations that get to something that's already known, but I get it in an entirely new way, which is the wave properties. For example, my model is predicting that the electron should have a gravitational radius, and the calculation, I'm not going to go through the details of how I get this. That happens next time. But the gravitational radius is Planck length squared divided by the electron's Compton radius. And then that number turns out to be the 6.7 times 10 to the minus 58 meters. This is an extremely, extremely small number, but it turns out that this works perfectly. Later I can show you all the things that all the places that it fits together. There's another calculation. Suppose we want to take the ratio. We have two electrons. They're gravitationally attracted and electrostatically repelled. And you then have a ratio of these two forces. So what is that ratio? Normally, when you calculate it, you use the gravitational equation and the electrostatic equation and divide those two numbers, and you come up with this number of roughly 2.4 times 10 to the minus 43. In other words, gravity is roughly 10 to the 43rd times weaker than the electrostatic force. But my electron model has got an amplitude that I'm just showing here is AS, and I'm not going to details of how it is. I'm just saying it's a wave property, and I take that wave property, I square it and divide it by the fine structure constant, and then I get the ratio of these two forces. And this isn't just me fiddling around with this. No, this is me looking at what this model is telling me and saying, okay, it should be this, and lo and behold, it works out right. Nice. And then there's a third thing I'm just telling you about, which is that the model also predicts that the electron is distorting the surrounding space-time, and it's making gravitational curvature, and the slope of the gravitational curvature is this Planck length squared divided by the electron's Compton radius, and then also divided by the distance. So how far away you go from the electron determines how shallow the slope is.
Oh, interesting.
And so this is, this comes from general relativity, and yet I'm not using any general relativity. I'm using wave properties. And so what I'm getting at is that there is many other things I'm going to tell you about where I can see how electrons, electrostatic force and gravity force are related. So, you know, people talk about, oh, someday we may be able to unify the forces. I can look inside this model and I say, oh, now it's like I'm the Wizard of Oz looking behind the curtain and seeing how the forces are related. So that's that's coming attractions. That's the next thing. I'm not really going to talk about that. I'm just setting up this, telling you it's worthwhile. This is going someplace that really I think is paying off. So anyway, now we can go away from these slides for a little bit.
Okay.
So we can go back to our screen.
Switch to
Good.
that.
Okay. So now that I hope I have your attention.
Yeah, you're very excited.
No, I'll tell you one thing here. This enthusiasm is something that goes on inside me as I'm inventing. In other words, you know, they talk about left brain and right brain is, you know, got certain things, including enthusiasm, love, you know, aesthetic properties and that sort of thing. Yeah. So enthusiasm allows me to get into the portion of the brain that's creative. So anyway, you can't help it. You get what you see when you're looking at me talking about these things. So anyway, then let's see. Hold on. I gotta. So the next thing I want to talk about is just overall in physics, there is many mysteries, and in fact, you know. Richard Feynman once said, if you think you understand quantum mechanics, you don't understand quantum mechanics. And he was saying, nobody understands all these mysteries of quantum mechanics that we have. You know, you have probabilities and you have particles discontinuously jumping from one place to the other, and a wave function that mysteriously collapses. And you have wave properties of particles and all these things that are mysteries. And so the idea is that, oh yes, the human brain just isn't able to understand these extremely difficult things that nature pulls off, and all we can hope ever to do is just mathematically write down the equations for them.
Shut up and calculate. Shut up and calculate.
Exactly right. Shut up and calculate. So I'm saying, no, you've been using the wrong model. Once you begin to think of the universe as nothing but waves, and I'll get to all of this, then you begin to find out that things that were mysteries when you thought of them as all particles and forces that were mysterious become all understandable when you think of them as all waves. So Let's see here. Okay, so the next thing I'm going to do is I'm going to talk about Einstein originally coming up with special relativity. And Einstein started off by postulating that the speed of light was constant in all frames of reference. And he also postulated like the laws of physics were the same or invariant in all frames of reference. Now, these were postulates. In other words, if you really say, what should Einstein have really been saying had he applied the known laws of physics, he would have said that rather than the speed of light being constant, he would have said, oh no, just like everything else, the speed of light should change depending on how fast you're moving. So just to make an example, suppose I have two detectors and I have a detector that's able to time as a bullet comes past here. I detect the first point and I detect the second point, and I time how fast it took, how long it took for the bullet to get between these two detectors. And then I can just measure the speed of the bullet. And then suppose that I want to calculate what it should be. And let's suppose the bullet is moving relative to my two detectors. So then I have to say, okay, I first of all am going to measure the speed that my detectors have, and then I have to introduce the velocity that the gun had relative to my two detectors. And once I combine these two, then I get the total speed that I should have seen. So anyway, then I didn't say that right, but I won't go back. But anyway, the point is that if you're dealing with light, all of a sudden that Galilean transformation where you add velocities and so forth doesn't work. Yeah. You say, oh yes, if I have two detectors for a pulse of light and I measure that it goes past the first one, goes past the second one, how long did it take? It doesn't matter how fast I'm moving the detectors, I get the same answer. Well, that's Einstein's postulate. And it turns out that you cannot get the special relativity. It's impossible to get special relativity without assuming the speed of light is constant, which is this postulate. So now there's been actually 3 technical papers written, and I talk about it in my only oscillating spacetime paper. These 3 papers said what type of a universe has to exist in order to be able to get not needing the postulate that the speed of light is constant, in order for the properties of the universe itself to be such that it automatically gives you that answer. Well, what they find is that if you imagine a hypothetical universe where there's only one field, and that field is an acoustic medium, and everything in that hypothetical universe is made out of sound waves. So it's kind of like, well, how can I make a particle out of sound waves? Well, you have to visualize in the simplest way. This isn't the way I'm going to get to it, but imagine you somehow had standing waves going out and coming back, and they somehow were organized so they didn't go anyplace. So it acted like a particle. Now it turns out these standing waves are kind of squishy. If I then start to move them, well, they don't have a specific distance. As I move them fast, the waves can start getting closer together, and I can get things where my rulers, which are made out of nothing but these sound wave particles, the rulers can begin to shrink. And I have clocks that are like Einstein's light clocks, which are measuring the time that it takes, except that rather than light in this hypothetical universe, you're just looking at the speed of sound in this universe. Mm-hmm. And you say, okay, well, I'm going to look at the speed of sound bouncing back and forth between the 2 reflectors here. And you find out that those sound clocks begin to have sound time dilation also. And so anyway, the point is that as you get into this, as described in these 3 papers, you find out that really the implication is we must live in a universe that is nothing but made out of a single field that it propagates light. I didn't say it right. Propagates waves.
Yeah.
And
Can I interject something here just for a second?
Yes, yes.
So because I work in the field of ultrasound, 3D ultrasound, I
Good.
completely understand the principle of the speed of propagation of a wave in a medium. Okay, so I did a similar thought experiment where like we make these phantoms that mimic the speed of sound of tissue, of human tissue, in order to do our to test our 3D ultrasound devices. And so I did a thought experiment where I took a block of agar, which we use, and I moved it, but I imagine that everything that all the people were inside the agar, and that agar is moving through space, but the speed of propagation of whoever is living inside this agar block is always going to be the speed of sound of agar, no matter what you did with this.
Oh.
Anyway, so I just wanted to throw that in there as I understand what you're talking about.
Okay, so yes, that's perfect. Because what they find in these papers is even if you do a Michelson-Morley experiment, attempt to measure the movement relative to the ether, if you want to call it, you find out that no, your instruments all compensate, and they, your rulers shrink, your time changes, and you cannot detect motion relative to this medium. And mathematically, they prove all this. So anyway, what I'm getting at is that I'm going to then skip on here to the next point, which is that I'm now going to say, okay, let's try and figure out what the single field is that we actually live in. And the first thing is that in 1950s, John Archibald Wheeler looked at the uncertainty principle and the vacuum zero-point energy. And he decided that all of that would be mathematically explainable if space-time was oscillating at Planck length. And I expanded his statement a little bit because he had it oscillating at all frequencies up to Planck frequency. I'm saying it's fundamentally oscillating at Planck frequency, but we get all these other lesser frequencies when we include a whole lot of these things, and then we add them all up and we get some lower frequency. So the point is that if I now take John Archibald Wheeler's idea that space-time is got Planck length oscillation, or the oscillations are expanding and contracting over Planck length, and these oscillations are happening at Planck frequency. So the first thing you find out is that if you multiply Planck length times Planck frequency, you get the speed of light. Yeah. So you have these oscillations happening at the speed of light. And very much like in sound, the speed of sound is determined by the velocity of the molecules or atoms in the gas. You get the speed of sound in this medium happening at the speed of these oscillations. So you've satisfied the first condition that I require. But then let's see, then we have other points that it's kind of like I then went further and I say, okay, if I'm going to really use this, I have to calculate other properties of this medium. So the next property that I calculated was the impedance of this medium. And this is calculated in the paper, and the impedance turns out to be C cubed over G. Now, C cubed over G is an enormous number. It's roughly 4 times 10 to the 35th kilograms per second. The units don't make any sense, but
kilograms per second could be thought of as mass flow rate. It's generally thought of as mass flow rate.
So yeah, there is another form of impedance, which is kilograms seconds and then per meter squared. And all it is that there's 2 different versions of what impedance can be, depending on whether you have your wave amplitude measured in length or measured in this dimensionless number that's a slope of a sine wave as across zero. So when people are working with gravitational waves, they have to use this dimensionless number because their measurement is how much does an interferometer measure over a certain distance, and that's delta L over L, which is a dimensionless number. So anyway, the point is that we end up then with the being able to calculate the impedance And also there's other things that gets calculated. There is a bulk modulus, and there is what I'm calling a virtual density and a virtual energy density. And the point, so right now there's something called the cosmological constant problem. And that is that there is a branch of physics, quantum quantum field theory, that says that the vacuum should have this enormous energy density, roughly 10 to the 113th power joules per cubic meter. Well, there's been like 300 papers written on this, and virtually all of them are written by people who say, wait a minute, I don't feel anything. This is crazy. This is the worst theoretical prediction in the universe, that you have 10 to the 113th joules per cubic meter. There's nothing there. And so, and yet I'm saying, wait a minute, I want to be able to have a medium that I am going to build the whole universe out of. This medium has to be really special. It has to be able to carry extremely, extremely high energy waves that can form particles. I mean, you know, if I not only form an electron, they can form a proton. Proton, yes, it's got 3 quarks, but it's roughly 10 to the minus 15 meters in radius. And it's got a lot of energy packed into that small. So the waves that have to be capable of doing this you have to have a medium with an enormous impedance in order for the waves to be able to achieve this. And as it turns out, the waves that I need all are limited by Planck length. In other words, so if I have my electron model, as I won't get into why I needed Planck length, except for the fact that that's the fundamental wave properties of the medium itself. And anyway, there is I won't go into one of the things, but anyway, there's various reasons why Planck length has to be the wave amplitude that I'm dealing with. So the problem then is, how do I explain away the fact that doesn't seem to be anything here? And that is that we are dealing with a medium that is missing a key component. And the key component is quantized angular momentum. So, for example, it's been well recognized that if you have a perfectly homogeneous energy density, you cannot detect anything. You can only detect changes in the energy density. So if you have a little rotating wave in an extremely high energy density medium that is lacking this rotating wave, all of a sudden, all you can really detect using the instruments we have right now is the rotating wave, which in my case is the electron, for example. So I'm saying that the energy density, that this 110 to the 113th power is virtual energy density, and you have to add in this angular momentum in order to make it observable. So that's, somebody else might say, well, I don't know if I really go along with that or not. Well, okay, but let's try it out and see if we can we make an electron out of this medium? So then the next question is, let's see, hold on, I need to go. So now I'm going to go and I'm going to start to look at the ways that waves can propagate in this medium. And for a moment, I have to take you to school, so to speak, a little bit on the properties of waves. So let's, can we go back to my charts here?
Yeah, I will put that back. All right.
Okay. Okay. So here we go, and I'm going to set this in motion. So this is just a boring sine wave, but obviously there's a zero line, there's an amplitude that is how high this is, and it's obviously moving to the right. We could have also made this moving to the left, and in fact, inside a laser, we have so here we have the blue line moving to the right like before, and we have the red line moving to the left. And now when we add these two amplitudes, we get this black oscillating line, and this is a standing wave. If you look at the points that's crossing the 0 point right here, it doesn't move. So this standing wave has got a stationary frame of reference, so to speak, in the sense that it's got nulls that don't move. So these standing waves have got not just the properties that you can see, but all of a sudden they have all sorts of new properties that you don't normally think of as associated with light. Here I am going to just for a moment just show you a standing wave, a higher frequency standing wave, because I'm now going to go to the next slide that's not moving. But this is like waves inside a laser. So inside a laser, you have two mirrors. Usually there's extremely shallow curve on this. And this is just capturing one instant in time. And this would be the graph of the oscillating electric fields inside the laser. In fact, there really is this nulls going on. When I've done experiments with lasers where I've been able to stick a dye-coated piece of glass in there, and I get this nice diffraction grating made because the waves erase the dye in every place that these amplitudes are in the antinodes, and leave the dye where in the nodes, so you get all these fine lines. So anyway, you have this standing wave laser. And now we're going to go and we're going to think about the things that can happen. Well, the first thing is it's kind of boring if we're just looking at it in a stationary frame of reference. But now suppose that we look at it in a moving frame of reference. So first of all, I'm going to simulate this by saying that the waves going two different directions, the waves going this way is a little bit higher frequency than the waves going the other direction. So now when I turn this on, this is what happens when we have two different frequency waves. And if I can try and hold my pointer here, you can see that, hey, those nulls don't move even when we have these standing waves, with waves moving like these waves. So it's like waves on top of waves. So these waves have got a wavelength. They've got a frequency at which these modulation envelopes are moving. Pardon me, not a frequency, a speed at which these modulation envelopes are moving. And then if we were physically to make this not by just having two different frequency waves, but by having a laser that's physically moving, when we physically move the laser, then as we look at it, we are looking at a moving laser. So we see Doppler shifted waves going this way and Doppler shifted increasing frequency this way if it happens to be going this way, and decreasing in frequency as it goes this other direction. So then we have two different frequencies just because we've moved the laser. So, this thing, it did illustrate one other point that I forgot that I had. So here I've also just illustrated the idea that we do have these standing nulls in here. So now I have a simulation of two laser mirrors, and you can kind of see these standing waves in here. So now I'm going to set this in motion. And once it starts moving, what I would see is something like this. If I could actually see the waves inside this, they would be moving faster than the laser is moving. And then when it comes to a standstill, it then gets back to just its oscillating standing waves that it had before. So it turns out that this is a simulation of it gets to the wave properties that an electron has. In other words, the de Broglie wave an electron has is got a wavelength. It's got then two different velocities. And when it's the wavelength is dependent on how fast the electron is moving. And just like these wave modulations are dependent on how fast the laser is moving, if I had the frequency in here equal to the laser's Compton frequency, then these wave properties would exactly be the same as the the de Broglie wave properties of an electron. So then all of a sudden I'm saying, okay, I have now learned something about what I want my electron model to be. In order to be able to achieve the electron's wave properties, I have to have a wave that is at the electron's Compton frequency in order to get this the wave properties right. So then let's look at this. Now I don't want to be carrying any mirrors around with me. So how am I going to get a way of having a single frame of reference for a wave? Well, one thing that can happen is if the wave is rotating, then you end up with a rotating wave has got a stationary center. It's got a specific frame of reference. So then the question is there such a thing as a rotating wave that somehow acts like a particle? Well, one thing I did here, I forgot so I just wanted to enumerate all the properties that the wave properties have in the moving laser. So first of all, there's a length contraction, which is that these high frequency waves right here go through a decrease in wave as it's moving. And this is the fundamental wavelength divided by the Lorentz factor, this gamma. And that's exactly what special relativity says that we have as far as the overall length contraction. Here is the modulation envelope wavelength. That's the electrons de Broglie wavelength. And then there's other things. There's a time dilation that's a little harder to illustrate in this way. There's also an increase in energy. And as you move this, you get waves moving this way is a higher frequency, the waves moving this way is a lower frequency. And you combine these two together and you get at low velocities, this 1/2 mv squared, and you get the relativistic increase on up to infinity when you approach the speed of light. So you get the correct kinetic energy. You also get the correct inertia because, as I said, the waves are applying pressure to the mirrors, and as the thing is accelerating, you get more pressure on the back reflector that's getting a blue shift, lesser pressure on the front mirror that's getting a red shift, and the exact inertia is then done. And then also, as I've already said, you get the de Broglie wave characteristics. So now I came to this question of how can I get an actual electron model? Is there anything in physics or known in physics that makes a wave into something analogous to a particle? Well, it turns out that inside a superfluid, if you add angular momentum to the superfluid, the angular momentum does not want to evenly distribute itself around the volume. In fact, if you take the most perfect superfluid is a Bose-Einstein condensate, and this is something that's extremely close to 0 degrees Kelvin. And what they do is they have a tiny droplet of this medium and the superfluid, and then they take 2 laser beams and rotate them, and they just rotate them for about 1/10 of a second, and it just introduces a very small amount of angular momentum. So when you initially introduce this small amount of angular momentum, you get little vortices that are kind of randomly distributed. But then after the first second or so, the vortices redistribute themselves into this type of a pattern. This is known, I forget there's a anyway, I forget exactly what it's called, a hexagonal something or other. I'll get it later. So anyway, here we have this picture, and each one of these black dots represents a small rotating vortex, and the hole in the vortex is only a couple angstroms in diameter. In other words, we're almost down to the size of the atoms that are making up this. So you're not really getting a picture of the vortex as much as they do some tricks with electrons or something like that to be able to get the vortex visible. So the point that I'm going to make here is that when I said that when you initially started to rotate this, you got a random distribution, and then it forms itself into this pattern. Now, this is the pattern that achieves the greatest distance between any one of these vortices. In other words, each vortex would make this pattern if it was repelling all its neighbors. If you had the boundary of the Bose-Einstein condensate here, and you said, okay, the vortexes can't go outside that boundary, and we're going to, in this one, I think they counted up 130 vortices. So if you have 130 of them here, what pattern if you put 130 electrons in a single plane and didn't let them escape and you bounded them, how would they arrange themselves? They'd arrange themselves something very much like this. So these are all repelling each other. And so each one of these vortices, it has h bar angular momentum. So here you have an electron having, in a single axis, it has h bar over 2, but then you over 3 axes, or whatever the word is, you have nearly h bar. Anyway, we're in the ballpark. We're getting things where h bar is this fundamental unit that makes these quantized units of angular momentum that then are then there's solitons. Now the word soliton is a word that I'm going to then, let's see if I no, I don't. I'm going to go to my last slide here, and then I'm going to talk about solitons. So I'm just skipping ahead to when I get to my electron model in the next time I'm here. It turns out there is a core that you have at the center here. You have a volume of space-time that has got slightly greater energy and slightly less energy, and it is rotating at the electron's Compton frequency. It is then, and the radius of this, the mathematical radius is this electron's Compton radius, is roughly 10 to the minus 13 meters. And it is disturbing the surrounding space-time. So then we end up with waves that are leaving, and we say that the reason that this particular frequency, the electron's Compton frequency, the reason it's stable is that it creates a condition that reflects its own wavelength. Just like creating a dielectric reflector that reflects a certain wavelength of light, the disturbances reflect their own. So then you end up with this type of a pattern. And as it's rotating, you get this thing. Even though these look like these are interference effects. These are actually rotating faster than the speed of light. But this isn't violating any laws of physics because this is an interference effect. And the part that is really the heart of this, that's really doing the work, is going at the speed of light. So anyway, this is, this amplitude should be falling off faster than is shown here. I just keep the amplitude up fairly high to illustrate it because it would decrease to almost nothing almost instantly. So anyway, the fundamental portion of these waves is going to create the electron's electric field. And then the nonlinear portion, this very much smaller component, is going to create the electron's gravitational field. And we then can actually get the forces between electrons, both gravitational and electrostatic, by using the mathematical properties of these waves and doing this. So I'm just saying this is coming attractions. So now we can go back away from these slides.
Oh, sorry.
Okay.
You got it?
Yeah, I'm finished here. So.
Oh yeah. Okay. So you want me to go back to this?
Yeah,
one?
yeah.
Okay,
So.
I was chatting with my sister in the background, so I was trying.
Okay, so
I was trying to get in.
Anyway, so let me look here for a second. So, kind of like the summary, I'm saying that the universe has got in space-time itself. Space-time is this marvelous medium that is vibrating at Planck frequency. And in fact, one version of this is that you have kind of like one portion expanding when another portion is contracting, and they're going like that. So you average out in the macroscopic scale, you don't think anything is happening, except for the fact that you discover that there's certain things left over from this. For example, it is physically impossible to make a measurement between 2 points that is more accurate than Planck length. And it's not just that your instruments aren't good enough. It is physically impossible. And what would happen if you were trying to make a measurement in a medium where you all the time have this little vibrations of Planck length vibrations? Well, it's going to screw up your measurement, and you're never going to get. Hold on, I got it.
You got a call.
No, I'm going to shut it off here. I can't. I know who this is. Okay, there we go. So anyway, you then have the
Now you lost your train of thought.
Yeah. So anyway, I'm saying that you have the vibrations of space-time causing it so it's impossible to make a measurement smaller than Planck length. So that's kind of a proof that there's something going on there. Also, the oscillation frequency, you can't make a time measurement that's any shorter than Planck time. It's physically impossible. And again, you have the vibrations. I haven't mentioned it before, but besides being a length vibration, there's also modulation in the rate of time. It's speeding up and slowing down by Planck time. And those two things then end up that when we then make an electron, we then create not only the electron's gravity as far as its acceleration, but we also end up with the time distortion that electrons are going to make, and the effect on spatial distortion. So anyways, then now we can stand back, and I just want to say, okay, now I'm going to make an argument that it absolutely has to be that space-time has got this type of a field in it. So I'm going to summarize certain things. First of all, I'm going back to my original point, which says that you never get Lorentz transformations unless you live in a universe that's based on sound waves, a sonic universe. But also we have all sorts of other hints and that we live in something that it's not just an empty void. So if you had an empty void, you wouldn't have like the permeativity of free space and the permeability of free space.
Exactly.
You know, imagine those numbers were either 0 or infinity. You could argue, oh, there's nothing there. But when there is some finite number, and then the impedance of free space, the impedance that a photon experiences, 377 ohms. Why isn't it infinite or 0? There's something going on there that has to be. There's something having to happen.
These are real physical properties that are measurable. So
yes, and so because people didn't have a model that they could put it to, they just ignored them. Oh yeah. Well, there's another thing that happens that to me is kind of like touchy-feely. If you make a laser gyroscope, so you have, let's suppose you have 4 mirrors that they make a beam go, and so the beam can go around the laser clockwise or counterclockwise, and then you beat these together, and as you rotate this whole thing, it turns out that those imagine you think of the standing waves in space. If you actually had like a waveguide, so you didn't have these corners, you just had this nice circle. Those standing waves in space are stationary. You take that waveguide and rotate it, and those standing waves don't move. And the laser gyroscope is telling you, oh yes, you just moved 1 wavelength, 2 wavelengths, or some very small fraction of a wavelength. In fact, just before I came here, I looked up what's the accuracy of a laser gyroscope. It's 100th of a degree per hour. It's better than the mechanical gyroscopes that are rotating. So there's something happening that there's this medium that the waves are moving, that you rotate the waveguide and the medium doesn't rotate and the waves stay exact. It ignores the fact that you have rotated it. So these are
all kind of like the magnetic field. When you take a magnet and you spin it about the polar axis, the magnetic field does not move.
Yeah.
And a lot of people call that a paradox, but it's not a paradox. That's just the way it works.
So anyway, the point that I'm getting at is that there is these things. So there's 3 other things that I really want to, I guess I got a couple more minutes here.
Yeah, sure.
So first of all, we have the constants C, G, and H. H bar. Let's talk. You don't like H bar, but I'm good.
It's fine. I understand.
Okay. So anyway, it turns out that people say, oh, there's no evidence that there's anything going on here. And I'm saying, no, the evidence that's screaming at you is you have these physical constants. And the physical constants, why is there a speed of light? Why is there a gravitational constant? And not only that, there's another really important thing. Tell me about time. What is time anyway? Now let's try to get a little bit more into the physics of time. If I'm in a gravitational field, it turns out that my lower hand here is experiencing a different rate of time than my upper hand. in the Earth's gravitational field, the difference is about 1 part at 1 second, 10 to the minus 16 seconds per second per meter. So this sounds like, oh yes, that's an enormously small number. But it turns out that this is really an extremely important thing that makes all these properties of gravity. For example, suppose that I had 2 protons, and the protons, even though they have 3 quarks, when you do a double slit experiment, you find out that the masses add together and they make a de Broglie wavelength that the proton has, or really de Broglie Compton frequency. So anyway, now I'm going to say, okay, now I'm going to take those 2 frequencies and I'm going to separate those 2 protons by a millimeter. What is the difference between those 2 frequencies because of the rate of time difference? Well, over 1 millimeter, those 2 protons are 25,000 hertz difference. And so it's now you have to think of every little segment of space having a different clock. The oscillations, in order to have time, you have to have every part of the universe have its own little clock. And so that it turns out that, I give you the example of the 2 protons, but the upper proton has got physically more energy than the lower proton. Now, in fact, if they were the same energy at the same level, they'd be at the same energy and the same frequency. And now I'm going to take and I'm going to raise one of them. And it turns out that the energy that I put in to raise it exactly was the energy that I required, that I can calculate out to change the frequency to make it this 25,000 hertz over 1 millimeter. If I raised the proton 1 millimeter, I then put that much energy in. So anyway, the point then is that when you then imagine the universe as having this oscillating space-time, now we have introduced a clock at every infinitesimal point of space-time everywhere in the universe. And you have different rates of time, and not only in different gravitational fields, but also in if I move differently, those clocks are moving differently also. And in fact, even there's another thing that I don't know if I'll get into, but maybe next time I'll talk about even the expansion of the universe. You know, everybody says, oh yes, look at that. We can measure the distance to a far galaxy, and it's moving away from us at half the speed of light, for an example. Well, there's another interpretation, which is that, yes, if we were to string a tape measure out there, that tape measure would tell us that it really was going at half the speed of light. But was the reason for that it's really physically moving away, or is my tape measure shrinking? Just like my ruler shrunk when I started to move it, or when I put it into a different gravitational field. So anyway, when you then you begin to say, okay, if the universe, for example, when people are looking at the Big Bang, they say, oh yes, we start with a singularity, and the singularity, you know, we have a Big Bang explosion, so to speak, and now we have to go through with all these contortions. Oh yes, we have inflation, and we're going to make speed of light expansion for a while, and then we're going to go faster than the speed of light, and then we're going to slow back down to the speed of light again, and then we're going to go even slower than that. And now if we tweak everything just right, we can kind of get it so that we kind of explain the universe as it's now existing, as opposed to, let's suppose that I say, oh yes, now give me the Big Bang where you now follow your 17 fields. How did the 17 fields react when you did all this? What were the 17 fields made of, by the way? So anyway, I then say, no, at the beginning of the Big Bang, you end up with space-time at its highest possible energy density, its Planck energy density. And I'll go into this a little bit later next time. But then it turns out that when you then start to expand this, you get the universe that we have today without needing any inflation, without needing anything. And so we have something that looks like a Big Bang, except that it was a wave distortion bang as opposed to little particles flying around. So anyway, I think I'm pretty well finished with this at exactly 5 o'clock, or 2 minutes to 5. So I'm ready for questions.
Okay, so I probably should start with my questions.
Okay.
of course, now I have so many things in my head, I don't know where to start. So one way I like to look at the Big Bang, I don't like to sort of say, oh, relativity is wrong or whatever. We don't have to say any of that, that's what I like about what you're doing and what I'm doing. I don't have to say that, oh, there was no Big Bang. But I like to see the Big Bang as a phase transition. Now, I'm just going to show you something.
Oh.
I'm going to share my slide. And we'll go back to your Bose-Einstein condensate image. Okay, so this is the most important concept, I think. This is another one of these pictures that I saw in your paper that made me want to look further, because I was already looking into the BEC, and because it's hard to say Bose-Einstein condensate very quickly, right? So the BEC was something that I studied many years ago, just because I was curious about it. And I was reading a paper by a guy named Don Hodson, who was talking about the universe being a BEC. And what he said was the universe began at the diametrically opposite thermodynamic spectrum at absolute zero. So if the universe is a BEC, then it could not have started at, the hottest, it started at the coldest. And so then you could imagine that the universe sort of warmed up or maybe spun up. So if the universe is a BEC, it spins up, and then you get your vortices forming, right? So this would be the medium before the Big Bang. And this is what actually happens in the BEC experiments when they raise it past a certain threshold temperature. Then, so you can think of these as balanced charges. Okay, so these little vortices are in balance, and that's why they're spreading out evenly, and they're forming these hexagonal, patterns. And so what I imagined is that so at a certain threshold temperature, and this is around 2.7 degrees Kelvin, which is the cosmic microwave background radiation temperature, around that temperature, unpaired vortices start to form, or unbalanced charges, which we could consider being electrons and protons, or your electrons and protons forming in the BEC, and they create an imbalance. And this phase transition, so you can think of this as a phase transition, is what we perceive as the Big Bang. So the Big Bang, I call it the big phase transition. I see the Big Bang as a phase transition in the universal Bose-Einstein condensate, where that is what, so there was a Big Bang, but it was a phase transition in my opinion. So do you have any thoughts on that?
Yes. Well, first of all, I also use the word phase transition. In fact, it's in that book, the Universe's Only Spacetime book. But I'm dealing with the opposite extreme, which is that it starts with the what I call Planck spacetime, which is spacetime. Imagine, you have Planck units, you have Planck force, Planck mass, Planck energy, and all these things. And in the beginning of that, all the parts of this Planck spacetime has got a value of 1. So you have like what will be photons, but at the first instant, the time of Planck time equaling 1, you have all of the photons. There's been no previous time. There's no gravity that has spread because there's no previous time. And you have the photons with Planck energy. All the forces are Planck force. All of the temperature is Planck temperature. And then anyway, as time starts to run, you end up, from general relativity, begin to expand to create new space, and you begin to have the loss of energy, or the transition from this Planck energy photon soup to more eventually you get to where we are today. So the reason that we don't need to have any corrections is that we started off with an absolutely perfectly homogeneous space. In fact, people have gone back and calculated. They said, okay, today when we look out at the universe, we're nearly flat space-time. It's within 1% of being perfectly flat. It might in fact be perfectly flat. And then they extrapolate back to the beginning of the Big Bang, and they decide that it had to match that to 1 part in 10 to the 60th at the beginning. So my model does that. I'm not sure your model does.
Yeah. Okay. Well, that's good. That's good. I have a question from the audience here. Glenn he says, very interesting, which it is. Does resonance play any role in this context? Now, my feeling is that the fact that it's all frequency based, the answer to this is yes, but I'll let you give
Okay.
your take on
So
it.
yes, I that's a point I didn't touch and should have. So resonances of everything. So for example, the reason we have a resonance at the electron's Compton frequency, I'm going to use radians per second. It's 7.76 times 10 to the 20th radians per second. It's roughly 10 to the 20th hertz. That's a nice round number. So it turns out that the reason why we have virtual electrons popping into and going out at the same time, in space everywhere, is that these oscillations that are happening in space-time happen to there's a resonance at that frequency. So you end up with these, groups of these oscillating, expanding and contracting, looking for a moment like they're electrons. They don't have any spin, and they don't last. They only last for
10 to the minus 21 seconds.
Yes, exactly right. Here we got it. So yes, so every particle that is a resonance if it's stable. So a muon is semi-stable and so forth. And let's see. Anyway, stability frequencies. In fact, even all of the transitions in like in a hydrogen atom. People say, "Oh yes, we have a quantum jump from the one orbital to another." Well, those are just two resonances that we're jumping between. There's really no reason why a point particle should want to jump to another specific frequency, but there's every reason why it wants to go to another frequency if that happens to be another resonance.
Yes.
So
exactly.
anyway, resonances are everything.
Exactly. So there's another question here. I'll just read it. There's a word here I really like called heterodyning. So could we potentially create waves of a readily tunable frequency from the background standing waves through beat frequencies, aka heterodyning? So this word heterodyning is really interesting. I read a paper recently on it, which I might share with you, having to do with the heterodyning of atoms in chemical reactions. So to increase the rate of, like, as a catalyst, using heterodyning as a catalyst. So I don't know if this word means anything to you.
So you didn't read my paper carefully enough. So
no, actually, I have a really terrible memory. So even
so in the paper, I have an example where I'm talking about. I go through various
in your paper or in your book? In
the paper.
Oh, really? I can't
Oscillating Spacetime. It's near one of the last sections right near the end, where I talk about a hypothetical experiment where you have an interferometer with two unequal path lengths. And I say, let's imagine that you have one arm being 1,500 meters longer than the other arm. So normally, if you just put white light in, or even just an ordinary light from a laser in, you would get that because of the difference in path length, you wouldn't necessarily get reliable constructive and destructive interference. But there are very stable lasers that if you put in the frequency of that, even one photon at a time, the physical length of the photon is much, much longer than 15 or 3,000 meters round trip. So I then say, oh, by the way, I've already done this experiment, so to speak, because when I was working in the aerospace industry, we were building laser radar systems that heterodyned. So you end up sending out, you make a type of an interferometer. We were using CO2 lasers. So you take a beam splitter, you split the beam, and you send most of the beam out to a target far away, further than 1,500 meters. You get back an extremely weak reflection. And then you beat that against a little bit of the beam that you sent out, or it's not the same. You didn't delay things by that distance. You got it. So you have this unequal path length that you're now heterodyning. And in fact, you can then you can get all sorts of wonderful a type of amplification that happens when you heterodyne with one beam much more powerful than the other. And you then end up, so I'm saying the fact that we were able to get this to work was already a type of experiment where you had one arm longer than the other arm by more than 1,500 meters. So anyway, I used the word heterodyning in that paper.
Okay.
Oh, now getting to the question he actually asked.
Yeah.
Okay.
Yeah.
So, so anyway, I think that what I'm trying to interpret, I'm not sure if he's talking about trying to heterodyne against Planck frequency. And
I think so. The background standing.
Yeah.
Yeah.
So, so it turns out that you can't get anywhere close to Planck frequency. It's like 10 to the 43rd hertz or something in that range. So, so anyway, hypothetically, I haven't thought about it, but I imagine you would be able, if you could physically do it, you could possibly get some sort of a result that might not be this nice clear signal, but might be this statistical type of thing that you say, oh yes, we somewhat saw it. But certainly, hypothetically, also as I was interpreting this, I was also thinking about trying to heterodyne against an electron, its standing waves, and I'm not. It'd be an interesting thought to see if we could figure out something there.
Is it possible that maybe the electron and proton are heterodynes of each other? That they are in tune with each other, that they are, frequencies related to the Planck frequency, and that's why they persist.
So you bring up a good point. The insight that I have had is that I believe everything that's stable, you make a hydrogen atom, each different energy level, and everything that's stable has reached a certain type of a harmony, a resonance. So, for example, I use a carbon monoxide molecule as an example of something that's physically rotating in space. I'm going to, during the next talk that I give, I'm going to talk about the electron rotating. And so far, the traditional physics says, oh yes, we have spin, but this isn't really a physical rotation. This is like an intrinsic rotation. Well, what does intrinsic mean? It just means it's there, but we don't know how it happens. It's like, and I'm saying, no, there's really a physical rotation. And you needed to say it was intrinsic because you were dealing with a point particle that couldn't possibly be rotating at this frequency. But when I'm getting a wave, and when the wave is only Planck length amplitude, then you can't detect this wave. And yet you can have physical effects that go on with it. So anyway, then anyway, I'm going to just leave it at that.
Okay, good. So the next question I have from the audience is, could the Bose-Einstein condensate be produced at the core of a black hole for a white hole universe be produced within a black hole universe, like nested dull black hole? So I think they're thinking of a black hole within a white hole within a black hole within a white hole. And I think that's maybe far away from you.
Yeah, no. Well, it's so hard to produce a Bose-Einstein condensate that, you need lasers, and you need the temperature that is lower than anything in the universe.
Yeah, so, I don't even know how they do that. It's amazing that they can do that. I'm always quite amazed. Okay, so the next one is, what is space-time made of according to this model? That's what this is about.
Yeah. So
now I have a companion question which goes with this question, because you use the word medium and you use the word field, and it seems like you're using them interchangeably, or do they have different meaning? The word, because you call it a field and sometimes you call it a medium.
Okay, so when I'm using the word field, I'm referencing the traditional idea that we have 17 fields. And so usually I then will say, no, I have, the one medium that I can also call it a field, if, in the sense that something is there that you can't grab a hold of. But unlike the 17 fields of quantum field theory, where they can tell you the value at each point, but they can't tell you the touchy-feely, what's the underlying physics that's going, why is an electron field different than a muon field? In other words, even, I have another question that I ask people that okay, you think you have the right answer. Tell me what the difference is between your model of an electron and your model of a muon. What is the physical difference? Because they're both point particles. They both have charge E. They just have different energies. Well, tell me how that works. How does that work? Well, I can tell you exactly what this is. And another point that's in the paper is that I'm saying that my model is predicting that the muon, which is 207 times more energetic than the electron, the muon's electric field, the percentage of the muon that is in its electric field is the same percentage as the percentage of electron. So then that implies that the muon has 207 times more energy in its electric field. And somebody can say, well, I know that's not right because I can do the experiment. They both have charge E. And I'm saying, no, it is exactly right, because the electron model has got one Compton radius. The muon model has got a Compton radius that's 207 times smaller. And if you calculate the difference in the electric field between those two, it exactly means that the muon had 207 times or 206 times more energy in that little spherical gap. Anyway, that gap in there.
Cool.
I went off track.
All right. Let's see. I don't know if we have any more questions here. I lost my train of thought because I thought I had a good question, but I think I lost it too. Okay, let me go back to my notes here. Let's see. Oh, yeah. I wanted to talk a bit about in your paper, you talk about the fact that when you use Planck charge and Planck mass and calculate the force using the, the calculations for the force, that you get the same value. And I did did some number crunching here and came up with this, what you see here, which you can see that I mapped it out and actually calculated why the force of two Planck charges, the gravitational force of two Planck charges is the same as the electrostatic force. And so I did the math to see that, yes, you're right, that these do in fact map out to these same, and it doesn't matter. I use H and you use H bar.
Yeah.
Right. You can see, I can zoom in.
So one of the things, by the way, is, let me just tell you a story behind all this. I started off telling you the story of how I came up with how I started all this. So as I was working on this paper, I would especially have students read it and then and then I'd ask them, tell me what it says. What did you get out of it? And I was disappointed to discover that one of the things that I thought was very important was that I was getting this connection between gravity and the electrostatic, electromagnetic force, except when I'm just going to call electrostatic since it's between two particles. So they weren't getting it that I had certain equations that I thought were screaming that, oh yes, look at how well this comes together. So finally it hit me that a way of explaining this was that in the limit of two Planck masses and two Planck charges, then in fact the forces are exactly, the same magnitude. They're opposite polarity if you have charges, but they're the same magnitude no matter what the separation distance is. And so then once I added that to the paper, then the students began coming back saying, oh yes, now I understand all this thing. So that one point was key to, it was like I wasn't explaining it enough. So once they understood this one concept about the forces being equal at this limit, then they began to understand it at all other conditions also.
Yeah, no, I think that's an important point. And I think that what you did there with working with these students, you told me the story about how you worked with these students and you wouldn't stop until they understood. And I think that's really great. So if they didn't understand what you're saying, it's just because you were saying it wrong.
Yeah, yes, I wasn't blaming them. I was thinking, okay, I am not explaining this. If they're intelligent people, they just don't get it. So I've done something
And
wrong.
so I think this paper that you wrote is quite an improvement from all the other ones, even though the other things I thought were good too. I appreciated them, but I appreciate this paper. I thought was very well written, and I really appreciate it. So there's one other thing I wanted to talk about in terms of Planck's Planck constants. Okay, which of course I use. Let me just go here. Sorry if I'm making people dizzy here. So the Planck natural units, right, which you calculate, which we calculate. You calculate using h bar. I use h. That's just me. But one thing I found was when you take these Planck units and you plug them into the units of an equation, like the units of it's like the gravitational constant. If you take the gravitational constant and write out the SI units, and then you plug in these values for in the SI units, if you plug these in, then you actually get the constant. So for instance, the speed of light is Planck length divided by Planck time. Or as you say, Planck length times Planck frequency. If you take Planck's constant, so here are the units for Planck's constant. If you plug in the Planck values, you get the right value. So it's just kind of a neat verification that these are in fact units, that these are unit. Gravitational constant the same, electric constant the same. The impedance of free space. Now here, this is a little different. When I take the kilogram per second meter squared divided by Coulomb squared, and I use, and of course I'm using H. So when I use H for my Planck units, I get this 29.97, whereas you get the different values. If you use H bar, you get the value that you mentioned earlier.
So yeah, but in fact, Planck impedance is the number that you say, which is this 29 ohms.
Yeah. And so, well, no, that's not necessarily, it is Planck impedance full, like the actual Planck impedance using the units of impedance. So, but the value that you talk about, the, you call it strain impedance. I think when you take the kilogram per meters cubed, okay, no, that's not the one. This one here. So when you take, there it is. So the kilogram per second is mass flow rate in the SI units. And when you take Planck mass and divide it by Planck time, so meters per second, or sorry, kilograms per second, we get your value for the strain impedance. It's interesting. You can just plug in the Planck units into the units as if it's an equation. Just plug it in, and you get the correct value for the constant. So I thought that was really interesting, and that's something, I've been working with unit analysis for years and years. I have books and books of me scribbling units, trying to figure them out, trying to tear the equations apart and figure them out using unit analysis. And so this is something that I discovered as I was playing around with units. Like I can just plug them in and, and get the correct constant. So
by the way, do you have any way of telling the size of the audience?
Teresa, can you see the size of the audience? I don't, because I had to shut down the YouTube because it was creating a feedback. So when I was actually trying, it was 32. So that's not bad, 32. So I'm kind of losing track of the comment section here. There's a bunch of people they're talking to each other as well. So in the chats, they don't assume that we have time to talk to them necessarily. And so they talk to each other, which is kind of cool. I like that. So yeah, so that's, that's okay. That's a good start. I think if we do this more often and more people watch this one, then they'll, want to tune in to another one. We may want to choose another night, like maybe a Tuesday night or something. Maybe Sunday's not good for family people. So it's really hard to pick a time because you've got time zones all over the world.
Are you going to have the video, the recording, so that somebody can watch it later?
Oh yeah, you'll be able to watch it later. Yeah, yeah. So it's live streaming now. Everyone can watch it now. But once we stop it, then it's in my on my YouTube channel, and anyone that goes to my YouTube channel can find
So
it.
we might advertise to the people that if we're going to do this again in 2 weeks, if they have any friends that want to see the next one, they could actually catch up by watching the recording.
Yes, exactly,
and then be ready for the next one.
Exactly, for sure. Yep. Yep. So, yeah, I don't see any specific questions. Let me just check my notes here. Oh yeah, so I think I showed this to you before, but I wanted to show my audience that I was able to replicate your, let's go to this one first. So the traveling waves with the standing wave. Now here I've got 2 traveling waves with 2 different amplitudes, and I'm showing the interference pattern, which is the blue, which is actually moving in a direction. It's not a standing wave because I've got 2 different amplitudes, which is kind of interesting. But this one here, where I replicate your modulation envelopes, I'm simulating the going a wave going one way with let me see, what do I have here? So 23 waves one way and 20 waves going the other way, so creating this modulation envelope.
So let me point out one thing
that I did. So I just want to show you that this is not just a sine wave or a cosine wave, but it's actually a helix wave.
Yeah.
You can look down the barrel of the gun of the wave itself with the helix wave. So anyways, I like doing stuff like that. So you're going to say?
Yeah. I forgot my there was a point concerning the, well, first of all, in this, it looks mishmash because you have, I think that the frequencies are probably too high. It turns out that, I know what I was going to say. So in these, each one of these, I'm pointing to one of the lobes or one of the modulation envelopes portions. There's a phase, 180 degrees phase shift between one and the next. So you don't get back to the original phase until you've gone through 2.
Okay.
So there is this thing with the Dirac equations where they have the Zitter-Bewegung, and I'm not sure pronouncing it right. And it is twice the Compton frequency for an electron. And I claim that the reason there's really no argument, because if you just look at the modulations, that's happening at twice the Compton frequency. But once you include the phase shift, then you get a fact, then you divide it by 2. So the Zitter-Bewegung and what I'm coming up with is really the same thing. And getting back to the fundamental frequency of the electron is the Compton frequency rather than twice the Compton frequency.
Okay, that's good to know. Yeah. And then there's this other animation I did, which has to do, which creates these torus structures, right? And then I've got these. So this might be related to the spin 1/2, right? The spin 1/2 of the electron. And maybe at some point we can talk about
that's a long discussion that I don't know if
I figured that might take up a whole
and it's more speculative. I can wave my arms, and what I can prove is that when you take my electron model and rotate it 360 degrees, it will not return to the same phase. But whether it's 180 degrees out and you go to another range, so I can't prove that it's going to come back after 720 degrees. Right. But I can definitely prove that it's not like a ball that if you rotate it 360, it gets back to the same condition.
Right. Yeah.
Essentially,
that could be related. I think
essentially you're moving waves, and the waves, as you're moving them, they have the speed of light problem, and so they lag behind.
I see. Yeah. It would be interesting if you could pin that down to if we can get an accurate replication of that in your model.
Yeah.
Let's see, what else do I have here?
Yeah, people, they go through these contortions where they have the ball and a bunch of ribbons attached to them, and you rotate the thing,
Yeah,
and you get,
yeah.
and that's a
And then
nice, it's a
they
nice
talk about,
model, but it has nothing to do with particles. There are no ribbons.
yeah, I agree. And so are you familiar with someone named Chantal Roth?
Yes,
Chantal Roth, yeah.
well, somewhat familiar. Yes,
Yeah,
she's.
yeah.
I'm in this discussion group,
Okay.
model of
Yeah.
particles, and she's in it also.
Okay, yeah. So she got in touch with me and she wants to form a smaller group to get into more detail into what you're doing. And she's very much into quaternions, and I have my own take on
Oh,
quaternions.
I would love to get in contact with her. So if you're in
Okay.
contact, or
Yeah,
tell her
yeah.
to.
She just got in touch with me like yesterday. So
Okay,
she
so she
definitely
just
is keen on starting a smaller group where we can really focus on
she
hashing this out. And
she just put something on Reddit about
yeah,
wave-based models of
yeah,
particles or something,
yeah,
and I
yeah.
noticed it right this morning as I'm preparing for this talk. So I
Okay.
said, "Oh,
Yeah.
had I not been doing this, I would have responded to
Yeah.
what she
No,
had."
she
But
knows we're doing this talk. She said,
okay,
like, I told her that, we're doing this, and she was happy to hear that. And so, yeah, she would like to do something, something more. I think a smaller group would be better. I know,
yeah,
like,
yeah,
I kind of get lost in the crowd when in these email exchanges, and I think we need to come up with a better way of communicating that. Like, I don't know if Reddit is right for
yeah,
us.
yeah, yeah,
I don't know. I've never done. I'm not
yeah,
even
yeah,
on Reddit, so maybe a Google, a Google Doc thing, a Google Drive, sharing a Google Drive
yeah.
and just sharing documents or something. Like, there's no really good way of doing this kind of collaboration. I wish we could all be sitting by a blackboard together and writing on the blackboard. I think those were the good old days when people actually collaborated in real life. And so she would like to do that. So hopefully we can do that in the next little while if you're
Okay.
interested. And I
If
think,
she, if she's listening, I got two email addresses. One of them is on the paper, so I'd like to get into
okay,
contact with her.
okay, I will tell her that if she doesn't hear, if she's not here right now. And yeah, I think that would be good. She seems really smart. I've watched the videos that she did, and she mentioned you in one of her videos on quaternions. And so I'm a big fan of quaternions, complex numbers and quaternions. I've been reworking them, so I want to talk to her about that because I know that she's keen on the quaternions. And so the quaternions, so the videos I showed you, the videos I showed of the, like, all this stuff I did with my version of complex numbers and my version of quaternions, so which are easy to implement on a computer. And so if you're doing anything with circular motion, like your spinning model, whatever, I also created your model. Where is it? I've lost. I have too many windows open. But this one here, I created your model using just a strange feature of quaternions, which I can explain to you sometime. It's kind of interesting, but this is my model of fluctuating space-time.
By the way, one thing
okay.
I didn't, well, as I've shown some of these models, I'll get into it in the next talk, but I have them spinning in one plane, but really it's kind of complicated where it's spinning in really three dimensions, and there's this distribution of how it goes and all that sort of thing. So it makes it harder to calculate things also if you're trying to say, oh yeah, we're going to predict
like
something.
Because these are all planar, like what I'm doing as well, and it is happening in 3D space, so it's a little harder to visualize that. It's tricky visualizing that.
Yeah,
So
yeah.
it's easier to visualize something in a plane. Computer screens are two-dimensional, and even three-dimensional stuff is really hard to display on a screen. And so but I would like to get my hands on the code. Chantel had written some code to model your wave model. Okay, right. She had written some code to model this guy here, just like you did in your video. And so, it's very CPU intensive. So you need a pretty good computer to run it apparently. So I'm going to try and get my hands on this code and, play around with it and see what I can find. So yeah, I think we're good. I think we're good. I don't.
By the way, with AI, I tend to think that AI is going to latch on to what I'm dealing with, because it really allows you to calculate things that you can't now calculate. And if you have enough computing power, you can begin to, for example, I'm going to just mention one thing. When I get down to predicting how an electron makes gravity, I believe that I haven't exactly worked it out, but I believe that it's going to turn out to be very slightly different from general relativity, not in any degree. In other words, you have a nonlinear expansion. So the third or fourth or fifth term in this expansion is going to be different than general relativity in a number that doesn't really count. but actually it might end up making the equation simpler. Everything gets, I found that when I'm dealing with waves, everything gets simpler. So I think that even general relativity, even the equations of general relativity might get a little bit simpler if you dealt with them as waves.
That would be nice. I would be happy about that, because I would like to understand the equations of general relativity without the complexities of the symbolic language. Is really difficult for me. I have trouble processing symbolic languages, and that's why I like my approach to complex numbers and quaternions is very straightforward. It's not symbolic at all. Like algebra is a symbolic language, and sometimes my brain just doesn't process. Like I've gotten pretty good at it, I think, over the years, but I had to work really hard at it. It doesn't come easy to me. And so anyway, anything you can do to simplify this for me would be really great.
I need help, so I'm not going to do the physical simplification myself. So
yeah, well,
okay,
we might as a team be able to figure it out though.
Yeah.
So,
okay, so you want to wrap this up?
Yeah, I think we did a good session here, and let's work towards maybe a couple of weeks from now. So we have a long weekend next weekend, so the weekend after that might be good to target. We can pin it down maybe in the next little while. We don't, within the next week, let's decide if we're going to do it in 2 weeks.
Okay, good.
And go from there.
Okay, well, thank you. It's worked out well. Good.
Yeah, it's great. So I'm going to end the stream, and then I'll say goodbye to my friends out there on the chat. And anyone in the chat, if you have any burning questions about this that I missed that you did today, or anyone else that has a question, put it in the comment section, and then in the next video that we do, we can maybe start by addressing those questions and then move on to the new stuff. Hopefully that sounds okay with you, John.
Okay.
Sure. Okay. Good. All right. Well, have a good night, and we'll talk to you soon.
Thank you. Okay. Goodbye.
Bye.